For the course Computational Tools for Economics and Management, and the topic for today is constraint optimization, which is basically when we want to optimize function and we have constraints. We will focus in particular on linear constraints, which are particularly well behaved, and it's quite easy to solve such problems using R. And linear constraints have the property that they can be written using linear algebra. As you see here, for example, they can be written as ax minus b bigger or equal than 0. I should emphasize that you must write the constraint in such a way so that R can solve this problem. And then we will spend some time in exploring how constrOptim is working. This is basically the R command in charge to optimize a function g when the constraints are linear. And we will see in class that there are other methods. Typically they are more involved than constrOptim to solve problems when you have non-linear constraints, and we will briefly see something about the so-called penalty methods. So the basic problem we would like to solve is a very simple one. We want to minimize a function, for example g. And you can see here that the problem looks pretty much close to the unconstrained optimization that we were dealing with last week. Basically, the only difference is that now we want to minimize a function over some domain D. Basically, there are some points x that are allowed. They are the points which belong to D. And of course, I want to find the x's for which g is minimum, provided that they are in D. So this is a very simple and clean notation, but let me provide a couple of concrete examples of the set D. For example, I may wish to minimize a function on the points such that x squared plus y squared is smaller or equal than 1. You may know that this is indeed the set of points inside the unit circle, which is depicted here in green. And so basically, I'm not really asking where the function g is minimized over the whole plane, but I am only focusing on the gray points. So this is exactly my constraint, or if you wish, D is the domain in which you are interested for this function g. Clearly, this is called a nonlinear constraint because, as you see, in order to write the set of points, the set of so-called feasible points, you must use squared. There are constraints which are simpler. For example, if you use only linear functions of x and y, then you can have other constraints. For example, if you assume that your feasible domain is described by x bigger or equal than 0, y bigger or equal than 0, and x plus y smaller than 4, then you end up in having this sort of piecewise linear domain. It is a triangle, and this is called the linear domain because in order to define D, you are just using linear functions of x and y. And this is exactly the case, this case here is exactly the case that we will focus on in what follows. So remember, you must be able to describe your domain using linear function in order to use constrOptim. So the boundaries must be described by linear function in x and y, and indeed whenever this is the case, you can write your domain using the linear algebra, and indeed you must do so. So let me provide a concrete example here. So assume that you want to write using matrix algebra this domain here. X is bigger or equal than 0, y is bigger or equal than 0, and then x minus 2y is bigger or equal than 0. Well, this can be written in matrix form as follows. You write a matrix in which basically you set the coefficient in the matrix equal to the coefficient of your constraints. So for example, the first row stands for the first constraint, and you see that there is a 1 times x plus 0 times y, which is exactly x. If you focus on the second row, for example, this will be there for the second constraint, And here, for example, you have 0 times x plus 1 times y, and that's exactly the second constraint that you see here. The third constraint is x minus 2y, and indeed 1 is the coefficient of x. 1 is the coefficient of x. Then you have minus 2 times the relative y here, which is going to produce x minus 2y. And as you see, you have an inequality bigger or equal than the right-hand side terms, which are 0, 0, 1, and that's exactly what you see in this vector here, where I am clicking right now. So basically, it is always possible to translate the standard constraints into a matricial form like this one, which is exactly what you need because you have to find the A and the B. Of course, there are more complex examples, and I would like to point out how to solve situations in which you have to work a bit in order to write the constraints in the proper form. For example, assume that you have x minus 1 bigger or equal than 0, y smaller or equal than 0, and x plus y smaller or equal than 4. So we have a set of problems. The first one is that we should bring the negative 1 to the other side, and that's exactly what we do here. The second and maybe more important problem is that here you have the wrong inequality. You should have bigger or equal, but here this is the first instance in which you say smaller or equal. And so we will have to find a way to translate this inequality in another inequality in which you see a bigger or equal sign instead of smaller or equal. And of course the same problem is also holding here. So the trick when you have to reverse an inequality is very basic and very simple. You should already be aware of this sort of basic and simple algebraic manipulation. Basically, you have to multiply both members by a negative 1. Whenever you do so, you can reverse the sign of the inequality, changing the sign of both terms. So if you multiply by negative 1 this inequality, you will get negative y bigger or equal. Take notice, I am reversing the inequality, negative 0, which is just 0. That's exactly what I wrote here. Of course, the same trick must be used here. So here I am multiplying this inequality by negative 1, and I get negative x less y. This is bigger or equal. I am reversing the inequality. I have a negative 4 here, as you see. And once you have written the constraints in this way, multiplying the second and the third row by negative 1, then basically you clearly see the matrix here. In the first row I just have x, this is why I just have 1 here, and there is a 0 for the y because there is no y in the first row. In the second row I just have y, and the coefficient of y is negative 1, and I have no x, and this is indeed the reason why I write an x here. And for the third row, as much as the third row is concerned, I have negative 1 and negative 1. So if you multiply this matrix times this vector of x and y's, you get exactly the left-hand sides of the inequalities which describe the constraints. And this is bigger or equal, as you see here, than 1, 0, negative 4. So basically this is how you can translate any set of linear constraint in the form A times x bigger or equal than some vector b. So once you have done that, you can use constrOptim. This is the command used by R to minimize a function g under linear constraint Ax bigger or equal than b. constrOptim is very similar to Optim, so you need an initial point. Of course, you need to provide one function. The function, exactly as it was the case with Optim, must be a function of a unique vectorial variable. So typically, you define g in terms of x and y, and as we have done in the past, you then define the second version, the so-called b version, gb, as a function of a unique variable. And moreover, you must also provide a description of your constraints, which basically boils down to provide the matrix A and the vector B. Let me stress a couple of very important things. So you are responsible to find the right matrix A and the vector of known terms B, and this is exactly what we have done before in a couple of examples. And moreover, there is another requirement for constrOptim. You have to guess an initial starting point for the optimization process, but in this case, the initial starting point must be inside your domain. Technically, we say that the initial point must be feasible. Sometimes you need some care in order to find an initial starting point, but usually this can be guessed, especially if you are able to draw a graph. So as an example to illustrate the use of constrOptim, I picked the following problem. So I want to minimize the function x squared plus y squared minus 3x plus y plus 2 with respect to the variables x and y under three linear constraints, which are x bigger or equal than 0, y bigger or equal than 1, x plus y smaller or equal than 2. Let me stress that this constraint must be manipulated in order to rewrite it in a form which is compatible with the standard way to write constraints for constrOptim, which is requiring to reverse the inequality as you see there. So I will initially start working to plot a graph of the situation. So here I am defining my function g. That's exactly the function x squared plus y squared and so on that you saw before. And then remember, exactly as we did for Optim, we defined the b version of the function. This can be done in several ways, but this is very handy because I don't have to type a lot once I have previously defined the g. And then I am defining a couple of sequences just to create a plot. This is a very standard thing that we have done plenty of times so far. You can use outer to compute a matrix of values of g for all the possible combinations of the x's and the y's that you were just defining, and you are ready to plot to plot the contour of the function g. As you can see here, they are sort of circles. And here I am also plotting the domain. So the small triangle that you see up here, is indeed your domain. This means that it is indeed the set of points that satisfy the three inequalities that you see here. So my question is really, which is the point inside the triangle such that my function g is minimized? And in order to solve the problem, I have to rewrite the constraints as I was telling you before. So my constraints are here, and then I don't have to do anything with the first and second constraint, but I must reverse the third row in order to reverse the inequality. So I have negative x and negative y bigger or equal than negative 2. It should be no surprise that you have a matrix A that you see here basically, and the vector B, which is 0, 1, and negative 2, as can be seen here. And we are now ready to use constrOptim. So constrOptim needs a matrix, which I am defining. So the matrix that you saw just a few seconds ago here can be written in R using the matrix command. So I was entering the elements of the matrix by row. So remember to write by row is true. And as you know, this is a 3 rows and 2 columns matrix. Then I am also defining the vector b, which was 0, 1, negative 2. And finally, I am ready to issue my command in order to minimize the function under linear constraint. So you must provide a starting point. I was picking a point which is inside the previous triangle. Let me maybe go back to this graph for a second. So I was picking 0.1, which is roughly speaking here where I click. And then I was picking as a y 1.1, which is again very close to the vertex inside the triangle. And then you give the name of the function. Typically we write null because you can provide the gradient of the function, but this is a sort of more technical development and we will not get into this. So typically you don't provide any gradient and you just write null and then you describe your constraints, providing the matrix A that was previously defined here and the vector B. And if you press enter, you get the results. So basically R in this case is telling you that the solution of your problem, the minimizer for your function inside the triangle, inside the domain D, is the following. It is pretty much the point 1, 1. Okay, it's very close to the point 1, 1. And in this point, your function takes the value 2 point something. That's a number which is very close to 2. And here you have additional information. So this is the first example in which we were able to solve a minimization problem under linear constraints. So I would like for a second to show you a better graph. So that's exactly the previous situation. I was sort of enlarging the levels so that you can see better what's going on here, and you see the domain in red. It is the same triangle that was depicted in gray before. So if you just look geometrically at this problem, you should realize that given the levels that you see here, I hope you can read them comfortably, given the levels that you see here, well, minimizing this function means which is the point at which my triangle touches a contour level for the small possible level. So here you see clearly that that this triangle touches several levels, but indeed the smallest level which is touched by the red domain is here. You have this point here, which is indeed the point 1, 1 that R was finding as a minimizer. And at this point, clearly the function must take a value, and this value is given by the contour level 2. And so basically this is confirming what we have found before from a geometrical point of view. This is confirming that the minimizer is the point 1, 1, because at that point your function takes the value 2, and this point is indeed in your domain, and it is not possible to attain lower values on this domain. Let me go back to the slides. So you can try to solve this exercise. I give you some time to take some notes. We will solve this exercise in the lecture, which is held on May 15, if I remember correctly. And in particular, you may want to draw the contours of the function, try to have a geometrical look at the problem. Then you can solve the problem once you have written your constraints in the linear form which is required. Basically, you have to reverse a couple of inequalities in this case in order to write the constraints as AX smaller or equal than B. And observe that this is pretty much very similar to the previous problem, but I was changing one constraint. So basically, I was changing this. So let me move forward now. So how do you use constrOptim when you have to maximize? Well, basically, this is exactly the same story as Optim. So there is an option. You may remember that you must add this option. So you must add control is a list in which fn scale is -1. And this is basically telling R that you want to reverse the scale of the function. So if you minimize a function with a negative sign, this is pretty much equivalent to maximizing the function, and this is the sort of technical information that R needs in order to maximize. And indeed, this is an example of what you get if you maximize. So I'm typing exactly what I typed before, constrOptim starting from a feasible point. I am maximizing the function GB, no gradient, so I write null, using the matrices A and the vector B that were previously defined. And here you had the option to let R know that you want to maximize. And you will get this maximizer, which is pretty much 0. This is 10 to the negative 10. So this is 5/10 of 1 billionth. So this is a 0, and then you have a 2, at which your function takes the value 8. Let me go back for 1 second to this graph. You may remember that maximizing this function from the geometrical point of view is equivalent to find the point in the triangle which is on the higher contour level, because I want to maximize. And it is pretty clear from this graph that if you want to touch this level curve here, the level, if you want to touch the level 8, you must go to this point of the triangle, which is exactly the point 0, 2. You see the 0 here and the 2 on the y-axis, which is the point 0, 2 that R was finding. So basically now you know how to translate your constraints and how to minimize and maximize functions of several variables, even though all the examples we have seen together are two variable problems. One final comment is related to a common error. I was sort of telling that a few times, but it is strictly required that the starting point is strictly inside the feasible domain. This means that it must satisfy all constraints, and moreover, the initial starting point should not be exactly on one of the constraints. So, for example, assume that I start from the point 0, 0. Let me go back to the graph. If I start from the point 0, 0, which is here, that's clearly outside of the domain. So if I start from that point, I am basically violating one of the conditions for the use of constrOptim, because, for example, the constraint that y is bigger than 1 is clearly not matched. And if you type constrOptim starting from that point, for our function using A and B, you will get an error, which is telling you what's going wrong. So basically, you were not providing the correct initial point. Keep in mind that the same problem would be there even if you leave y equal to 0, for example, because remember that the initial point should not be on one constraint. So given that we had x bigger or equal than 0, you should pick an initial x which is slightly bigger than 0. And indeed, this was the reason why I was picking 0.1. So I have a constraint that x must be bigger than 0. So for example, 0.1 is clearly bigger than 0. And I have another constraint telling me that the y should be bigger or equal than 1, but I cannot pick 1 because that would be exactly on the constraint. So I am slightly increasing the initial y to 1.1. And this is pretty much all I have to say about constrOptim. Thank you for your attention and see you in class.